Good morning students, I welcome you all for another lecture on the course Computer Architecture and Organization. In today's class, I am going to discuss about concept logical instructions. So first of all, what logical instructions are? Right? These logical instructions are used to perform logical operations. I repeat. The logical instructions are used to perform logical operations. The basic logical operations are AND, OR, and NOT. We know that these three are the basic logical operations based on the STLD concepts. We can understand what logical AND is, logical OR is, and logical NOT or complement is. To do this logical operations, we took the help of logical instructions. We know that the internal circuits of a computer system are designed with the help of logic gates. We know that. That means the hardware devices are designed with the help of logic gates. The logic gates are the basic elements to make any hardware device. By using software instructions also we can perform logical operations, that is logical AND, logical OR, and then complement. In this class we are going to discuss about those logical operations in more detail, how we can go and do the logical operations with the help of logical instructions. So one more thing is these logical instructions we can also call as bit manipulation operations or bit manipulation instructions. So here these logical instructions are also called as bit manipulation instructions. What is the meaning of this? The meaning of this one is, what are the bits if you want to manipulate? That means what are the bits if you want to change? Only those are corresponding bits we can manipulate without changing the rest of the bits which are present in a word or a byte. I repeat, the bit manipulation instruction means changing of bits. What are the bits if you want to change, or what are the bits if you want to manipulate in a operand or in a byte or in a word? Only those particular bits we can manipulate with the help of these logical instructions without disturbing the rest of the bits which are present in that operand. So that is the meaning of bit manipulation. So here the logical instructions we can also call as bit manipulation instructions. That you have to remember. Next, these logical instructions perform logical operations on all the bits which are present in a word or in a byte, parallelly or simultaneously. Sometimes we can go and change only few bits of in a byte or a word. According to the requirement, we can use the operands in the instruction. Because at the beginning what I am saying is, bit manipulation instruction means what are the bits if you want to change only that particular bits we can go and change without disturbing the rest of the bits. But here I am saying one more statement regarding this logical operations is, these logical instructions are used to perform logical operations on all the bits which are present in the operand, that means which are present in byte or word simultaneously. So that we have to remember. We can go and see some of the examples. So the first one is, this is an example, and R1, R2, R3. The meaning of this instruction is perform logical AND between CPU registers R1 and R2 contents. After completion of logical AND, the result stored in another CPU register which is R3. Let me assume friends, R1, R2, R3, 3 are the some 8-bit registers. Here R1 contains a value some 89H, and R2 contains a value F0H. I am already told you clearly, in the system, the numbers are representing only with the help of hexadecimal numbers. You remember them. That's why here I was using R1 content is 78H and R2 content is F0H. In this instruction, what I am doing is, I was doing a logical AND between the content of R1 and R2 bitwise. Go and take a binary equivalence of this R1 content. 78H is nothing but 0, 111 and 1000. That is the binary equivalent of 78H. And second one is F0H. Its binary equivalent is 4 ones and then 4 zeros. In this instruction execution, simply we are going to do bitwise logical AND. We know that for the inputs of an AND gates, both are logical 1, then and only output is 1. For remaining cases, the output of AND gate is equal to 0. We know that. So, if you remember that, here both inputs are 0, 0. So, output is 0, again 0, 0. And one is ANDing with a 0, output is 0. One is ANDing with 1, 1, 1, 1 and again 0. Finally, here our result is, it is equal to 70H. This is the final result after completion of this logical AND. This 70H was copied onto register R3. So, 70H goes to another CPU register, which is R3. So, if you are observing guys here, bitwise logical AND was happened between the contents of register R1 and register R2. So, like this we can do logical AND in the computer system with the help of this particular instruction. Similarly, I can go for another example how a system can perform logical OR. So, this is my example instruction OR R1, R2, R3. The meaning of that one is do logical OR between the content of R1 with R2 bitwise. After completion of logical OR, the result was stored onto another CPU register R3. Let you can go and take again example. Here also my assumption is R1, R2, R3 all are 8-bit registers. Let you can assume R1 value is some 89H and R2 value is some 23H. So we know that logical OR properties, that is if one of the input of R8 is equal to 1, irrespective of other, output becomes 1. You just follow that. So take binary equivalent of 89H, it is equal to 10000 1001, and similarly for 23H, it is 0010 0011. Do logical OR bitwise simultaneously. Here it is 1 1 0 1 0 1 0 and 1. Here what the result is? Here the result is equivalent to A, B, H. After completion of logical OR between the content of R1 with R2, we may get a result is ABH. Finally, that was copied onto another CPU register R3. So this is ABH. This is the way how internally OR R1, R2, RT instruction was executed. And similarly, I'll go for one more example how a system can perform XOR. So XOR space R1, R2, R3. The meaning of this instruction is do logical exclusive OR between the content of register R1 with R2. After completion of bitwise logical XOR, the result was stored into another CPU register R3. So just you remember again friends, logical XOR operation. In a logical XOR operation, if the inputs are differed, that means the inputs of XOR gate is not same, then output is equal to 1. If the inputs of XOR gate is same, output is equal to 0. Just you remember that by using that logic. internally XOR operation can be performed between the content of R1 with R2. Again, I take an example. R1 is equal to some 79H. R2 value is some 63H. Take binary equivalence of this. 7 is 0111, 9 is 1001. Coming to 63, 6 is equal to 0110, 3 is 0011. Do logical XOR operation between these two data bitwise. Here the inputs are same, output 0, inputs are default, so on same, default, same. Here finally the result is 1AH. So after execution of this particular instruction, the result was 1AH, then finally copied onto another CPU register R3. R3 value is 1AH. If you are observing previous three examples, that means logical AND operation, logical OR operation, and logical XOR operation, we did these operations in parallel in the operands. That you have to remember. So finally, how I can go and perform a complement operation or a NOT operation? Everyone we know that NOT operation is also called as inversion or a complement. And one important thing is this NOT operation is called unary operation, and our previous three operations are binary operations. So don't confuse the friends. Previous case also I did logical AND, logical OR and logical XOR only on binary data. So that's why I was calling those are the binary operation. That is not true. Binary operations means to do a particular operation we need two operands or two data. That's the meaning of binary operation. Here I clearly says that NOT is nothing but unary operation. Complement is nothing but unary operation. Inversion is nothing but unary operation. That means you have to do this particular NOT or inversion or a complement, we need only one operand. So that operand is act as a source as well as a destination. So that's why here my example is like this, NOT R1. That means complement bitwise the content of the register R1. So again my assumption is R1 value is equal to some 89H. Before execution of NOT R1, its a binary equivalent is 1000101. If I take a complement for the bits which are present in register R1, the data is changes to like this: 0111 0110. Now after execution of this NOT R1, this is the value that was present in register R1. What is this hexadecimal equivalent? It is a 76H. The 76H again goes to our CPU register R1. I hope you understand. Logical AND, logical OR and logical XOR, these are called a binary operation. That means to do these operations we need two operands. And one more similarity is, what are the operands I was using for these are three types of instructions? The operation was done in parallel. But coming to the fourth one, that is a NOT operation, is called a unary operation. In this case, to do an operation on the operand, I just need only one operand. That operand is act as source as well as a destination. Right. And next thing is a shift and a rotate instructions. This is a very important thing to us. We frequently use shift and rotate instructions in our systems or in our regular operations. So these are shift and rotate instructions are simply used to perform shift and rotate operations. I repeat, these are shift and rotate instructions are used to perform shift and rotate operations. What is the shift operations and what is the rotate operations? So let me try to find. One thing you remember, rotate operations is also called as circular shift operations. Do you remember that? The another name of rotate operations are circular shift operations. You remember that. And there are two types of shift operations we have. One is logical shift operations and second one is arithmetic shift operations. I repeat. So rotate operations are also called as circular shift operations. And there are two types of shift operations. One is logical shifts and second one is arithmetic shifts. Now I can go and discuss about these logical shifts, arithmetic shifts, and then circular shifts in more detail with the help of examples and diagrams. Please watch carefully, right? So first one is logical shifts. In these logical shifts, there are two types of logical shift operations we have. One is logical shift right and second one is logical shift left. One type is logical shift right and second one is logical shift left. These are the two types of logical shifts we have. Basically, these logical shifts operations are helpful to us to do the arithmetic operations, multiplication as well as division in a faster way. I can say like this: logical shift left operation is helpful for me to do a multiplication, and logical shift right operation is helpful for me to do a division operation. How I can perform these two arithmetic operations, that is multiplication and division, with the help of this logical shift right and logical shift left, we can try to identify. I will try to learn this with the help of some examples. So first I discuss my discussion with the logical shift right. In this logical shift right operation, what are the operand? I have a data. The data bits are shifted to right side by n number of times. That means count number of times. I repeat, in this logical shift right operation, the data bits are shifted to right side bit by bit n number of times or count number of times. For better understanding this, I took an example: L shift R space #2 comma R0. The meaning of this one is, here L represents logical. Here L represents logical and this R represents right. So now the meaning of this one is logical shift right. The content of a CPU register R0 by 2 times. This hash indicates count value. Let you can assume this is your register R0 of size some 8 bits. It is like this. This is our R0 of size 8 bits. Initially R0 value is 101110 This is a value initially that was present in register R0. In the execution of this particular instruction, logical shift right #2 comma R0, that means the content of this register R0 shifted to right side by 2 times. So then what happens? The bits are moving in this direction. That means we know that this is the most significant bit MSB and this is least significant bit LSB. If I shift one time this bit, what happens is, here at the most significant side bit position was vacant. Now you remember, so in this case this vacant bit position is filled with 0 and in another end I was losing a data. In that process, if I shift to first time, the content of this R1 is changes to like this. So here the bit is 0, this bit was shifted to this 1, this is moved to here 0, this bit is moved to here 0, this is moved to here 1, it is moved to here 1, it is moved to here 1, and it is moved to here 0, and this 1 goes off. After one time shifting, the content of a same register R0 is changes to like this: 0100 11110. If you do one more time, what happens? Again this bit was shifted to here and this bit position is vacant, that is again filled with a 0. Next this one shifted to here, the 0 here, the 0 here, 1 1 1, and this 0 goes off. Now what's the value of R1 now? After execution of L shift R #2 comma R0, the content of R0 is equal to 0010, it is equal to 2, 0111, which is equal to 7. That means after completion of this particular instruction execution, the content of register R0 is goes to 27H. I hope you understand how the data bits are moved. And one more interesting thing is in this logical shifts, out of the bit that was left from the register, that bit is right away goes to carry flag. That bit is directly goes to carry flag. We know that carry flag is one of the condition code which is present in condition code register or in a flag register. Whatever the bit we are last from the register, that bit is right away goes to carry flag. Whatever the bit already exists in a carry, that is left from that carry flag. So this is the way how we can do logical shifts. So here I took an example. So see carefully. For example, R0 value is some 20H. R0 value is 20H. So if you take bind equivalent of this, 0010 and then 4 zeros. If I shift right one time, this what happens. This is changes to 0001 and upper nibble is as it is 000. What is its equivalent hexadecimal value? This is equal to 1 and this is equal to 0. That means here what happens? Your input value is this 20H. After one time bit data was shifted to right side, then what happens is the content is decremented to half. That means the input data is divides with the 2. The input data is divides with 2 because 20H by 2 is equal to 10H. Similarly, if you shift this data to one more time left, your data is this is 10H. You do one more time right shift, then this is changes to 4 zeros and this is changes to 1000. Then hexadecimal equivalent of this is 08H. So input is 10H, output is 08H. Now 10H is divides with a 2, no doubt the resultant is equal to 08H. How it possible? In hexadecimal, 10H is equivalent to decimal 16. We know that. 16 by 2, it is equal to 8. Here the condition satisfies. So based on this simple logic, we can understand that a logical shift right operation is equivalent to division with a 2 operation. That's important. This is equivalent to division by 2. This is important. In a similar way, how we can do logical shift left. So this logical shift left operation is exactly opposite to logical shift right. So in this case, the data bits are moving from left hand side, right hand side to left hand side. So here my instruction is L shift L. Here similarly in previous case L represents logical and this another L represents left. So the full meaning of the instruction is logical shift left the content of register R0 by 2 times. That is the meaning of this. Again I took an example. Register R0 value is equal to 08H initially. Again this is register R0 which is an 8-bit register. Initially it is loaded with 08H. It is like this. We know that here it is LSB and this was MSB. In this logical shift left, the bits are moving in this direction. In this direction. So then if I shift this data to one side one time, so then this bit was moved to this is 0, this is moved to here 0, this is moved to here 0, this is moved to here 1, 0, 0, 0 and this bit goes off. Whatever the bit here we are goes off from the register, that is a straight away go to the carry flag. At the same time there was vehicle was created at LSB that is now filled with 0. That is filled with a 0. Now what is hexadecimal equivalent? This is equal to 1 and this is equal to 0. That is 10H. Your initial data is 08H. After one time left shift, the resultant is equal to 1 0. You do one more time in a similar way, then it is again changes to 0 0 0 0 0 1 0 0. Is the same logic. Then what is the hexadecimal equivalent now? It is 20H. Are observing or not, guys? In previous case I took the same example for explanation of logical shift right. At the end I conclude that logical shift right is equivalent to 2 divided by 2. But now it is exactly happened in opposite way. This logical shift left is equivalent to 2 multiplied by 2. That is an important. Because initially 8, 0, 8 into 2, that is 16. In decimal converted into hex, it is equal to 10H. Again 10H is multiplied with the 2, result is equal to 20H. So based on this logic, logical shift left is used to do a multiplication and logical shift right is used to do division. I hope you understand what the logical shifts are. In the next class, I am going to discuss about arithmetic shifts as well as circular shifts. Thank you for patient listening.